right, everyone. So let's go ahead and get started with uh, with our review of mathematical concepts that we had begun last time. Before I begin, any particular questions about the parameterization stuff that we covered last time? Um, so very quickly, if you remember, we said that there's an essential difference between physical quantities and their mathematical description in terms of components. Any physical quantity does not need a coordinate system to be defined. But if we want to work with those quantities mathematically, it's easier to set up a coordinate system which comprises an origin and three unit vectors which have to be abstract. You can't really define how these things in terms of something else. But once you do that, you can describe geometrical objects, lines, curves, surfaces, and so on. And we also looked into the notation for scalars and vectors. And I showed you a precise notation in which we will be working with vectors. I think that bears repeating here. If we have a vector v, we are going to, of course, denote that with an underline. In terms of components, v1 is a scalar. It's the component along e1. v2 is a scalar along e2 unit vector, and so on. And when you add them up, you, of course, get a vector. So that's why I can write it as an equal to sign. Whereas I cannot write this vector to be equal to three numbers, right? So we have to be careful about that notation thing. The vector v can be represented with these three numbers, but it's not equal to these three numbers. So that's, I think, where we were about last time. Couple of notes here, as it says in your notes, the position vector we are used to calling, at some point in space, say point P has some coordinates. We say the position vector of that point is the vector that goes from the origin over to that point. Now, is that a vector? Is that a vector in the way that we have defined it? A vector is something that has magnitude and direction, and it is independent of the coordinate system, choice of coordinate system. However, if a position vector inherently depends upon your choice of coordinate system. If I choose a coordinate system here, I get one position vector. If I choose a different coordinate system, I get a different vector. A position vector is not technically a vector, but most often, quite often, what we'll do is we'll fix the coordinate system and we'll say that we'll use only this coordinate system. And then for all practical purposes, the position vector behaves like a vector. So we are able to use all of the vector operations on position vectors as well, vector addition, vector multiplication, and so on. That works, but technically, position vector is not a vector. In the same way that we have scalar fields, you remember we talked about temperature at a point, density at a point of a body. In the same way, vectors also occur as fields. And for example, I could have a body that could be going with a constant or uniform velocity. Each and every point of this body may have the same velocity, or I might have a deformable body. There's no deformable body. If this deformable body is kind of flexing and rotating and translating, then each and every point of this body has a different velocity, which means that if you were to plot the velocities of each and every point in that body, different points will have different velocities. And of course, that means that what we have is a velocity field as a function of x, which is the position of the point. Similarly, a distributed force field, for example, the body force, this B of x is what I'm calling, this is really what we'll see later on as well, is it's a body force, which means that anything that has volume and mass is going to experience a body force like a gravitational force. Or, for example, if it's a magnetic material, then each and every point of that body is being pulled or pushed by some force, that is a distributed force over volume. So those types of forces, these are all fields. This is a force field, really. Okay. Um, so I think these things will be clear as we go on further into the course. But just to keep things in mind. So let's see how um, vectors operate with each other. These are simple operations. I know you obviously know all of these things, but what we'll do is to use these simple operations to understand the notation and some of the basic operations that we are going to use. So for example, if I want to do vector addition without reference to any coordinate system, so that's another thing uh, I should mention. On the right hand side of this blue line, I'm going to express the same operation with coordinate systems, with E1, E2, E3. On the left hand side, we are going to express the same operation without reference to any coordinate system. So if I want to add two vectors, how do I do it without using any coordinate systems? Say that again. Okay, yeah, it's a parallelogram law. Very simple, nothing very tricky about it. What we do is we draw a parallel line from one end of U to and from the other end of V parallel to the other vector, and then once we have that, we connect the tail of those two vectors to the head of where they intersect, and that indeed is U and V, U plus V. And the important thing to note here is I did not use any coordinate system in this vector addition. Vectors don't depend upon coordinate systems, so any operation on them should also not depend upon any coordinate system. Okay. Whereas if I were to use a particular coordinate system, this E1, E2, E3, then I could express this as U1, E1. U1 is, and similarly, U2, E2 plus U3, E3 plus V1, E1 plus V2, E2 plus V3, E3. No surprises there. Just keep in mind that I'm underlining all of these unit vectors, and the scalar components are not being underlined because they're not vectors. And of course, I can combine them and write it as U1 plus V1 E1 plus U2 plus, sorry, V2 E2 plus U3 plus V3 E3. And what would be a shorthand notation of this?
Sigma I C3.
Okay.
Then we have UI plus VI.
Okay, so UI plus VI. Anything else? Yeah, EI, right? Right. So that would be a shorthand notation of the same thing that I've written in expanded form. Just adding two vectors, there's nothing special about it, but note that how we are working through this in this shorthand notation, that we'll go in much more detail very shortly. So the point is that this type of notation helps us to write long expressions in a very compact way, and we'll actually make even further shorthand notations on top of this. So couple more properties of vector addition. In fact, subtraction is nothing but the addition of a negative vector. So if I am trying to do u minus v, I have these two vectors u and v. I'll compute what is minus v, just the negative of that, and then add them in the same way. So u minus v is just u plus minus v, something that you know. And if I add these two vectors, if I take u and add it negative u, of course we get 0 vector, note that there is an underline between 0 as well, because on the left hand side I have a vector. I have a u vector and a minus u vector. When I add two vectors, I better get a vector, even though it is a 0 vector. I cannot write u plus minus u is equal to 0 scalar. Okay. Um, and finally, you're obviously familiar with the properties of vector addition. First, u plus v is equal to v plus u, which is called the commutative property, and the other, that if you have three or more vectors, you can add them in any order you want. That's the associative property. So all of these things are well known. I'm sure you all know this already. Let's look into some vector products. Okay. The first type of product is just scalar multiplication of a vector. So if I have a vector u, and if I try to multiply it with a scalar, all it does is it changes its length, right? Physically, a vector is something that has magnitude and direction. So scalar multiplication, all it does is changes its length. The direction remains the same. And yet again, I have not used any coordinate system to define all of this, right? So, but if I were to use a coordinate system, then I can express the vector u in terms of its components. And of course, the shorthand notation would be I equal to 1 to 3 of ui ei. And if I were to multiply it with a scalar alpha, alpha times u can be expressed as what? How? So I could write alpha outside, or I could just say that it is I equal to 1 to 3 of alpha ui ei. Essentially, alpha is multiplying each and every one of those scalar components, scaling the entire vector by that amount alpha. If alpha is negative, the vector changes direction. If alpha is less than 1, the vector shortens. Alpha is greater than 1, the vector elongates, right? So no worries about there. But I would also want you to start noting something here, that whenever we are writing this summation sign, every time that we are writing this summation sign, I is equal to 1 to 3, it looks like we have two i's in the term that is being that we are using this summation sign for, right? Every time I write the summation sign, there are two i's. There are two i's here, and you'll see more and more examples of this, that which is actually called a repeated index, and we'll come into that in a little bit. But this is something to note here. All right, dot product, no worries there. Go ahead, Amit.
Before we go to the dot product,
Sure.
if we multiply by a negative number,
Mhm.
We will get the opposite direction, right?
Yeah, the direction will change. The orientation would change, but not the direction, I would say. Right? The orientation is in which direction it is pointing. Of course, it will flip, but the direction is still the same. You're right. Okay, so dot product of two vectors, again, without any coordinate system, is defined as the magnitude of u, magnitude of v, times the cosine of the angle between them, right? These are all physical quantities. Magnitude of u, v, and the theta between them, these are all physical quantities. No need to use a coordinate system to describe them. And this, of course, is a cosine identity that hopefully you all remember, that u dot v can be expressed in terms of this cosine identity. And how do we find the magnitude of a vector itself? We take that vector u and dot product with itself, and we take the square root of that, would give me the magnitude of that vector. So these are all physical without reference to coordinate system description of the dot product. And on the other hand, if I were to use a coordinate system, E1, E2, E3 with some origin here, I have two vectors. Now I want to do a dot product between them. So in order to do the dot product with coordinates, let's see how we can do that. We already know how to do that, but let's see using our notation how to do that. I will write u as the sum of ui ei dot right here, and V as the sum of Vj Ej. Now, one thing here is that for the first summation, I use I. For the second summation, I use J, just so that I can distinguish between these two different sums. I don't want to be using the same index I again and again and again in different terms. Okay. Um, so obviously, this will look like U1 E1 plus U2 E2 plus U3 E3. And I'm going to make you write all of this out so that you get tired of it and you're going to want to use the shorthand notation that we are going to develop. V1 E1 plus V2 E2 plus V3 E3. And how many, if I were to expand this, how many terms would I get? 9 terms. All right, let's begin. So we'll have U1 V1 E1 dot with E1 plus U1 V2 E1 dot with E2 plus all right, U1 V3 E1 dot with E3 plus U2 E1 E2 dot with E1 plus U2 U2 V2 E2 dot with E2 plus U2 V3 E2 dot with E3 plus U3 E1 E3 dot with E1 plus U3 V2 E3 dot with E2, and finally U3 V3 E3 dot with E3. In all of these, note that E has to have an underline. V and U components must not have an underline. So no matter how long the expression is, you have to be very careful with all of these things. And indeed, we do not want to be writing these types of long expressions over and over again. So we are going to come up with a slightly shorthand way of dealing with things. What we're going to see is that a lot of these terms are 0. Why? Because, let's see, I'm going to say E1 dot E2 is 0. These are two unit vectors that are perpendicular to each other. E1 dot E3 is 0. Similarly, E2 dot E1 is 0, E2 dot E3 is 0, E3 1, and not E3 3, but E3 2 is 0. The only non-zero terms in this expression are this first one, U1 E1 and U1 V1, and then the other two non-zero terms are U2 V2, and finally we have U3 E3. So this will happen quite a lot. This will happen in quite a lot in several expressions that we are going to deal with. So to go ahead, April.
In the second and third row in this column, you have U times E instead of U times E.
Sorry, that should be indeed U1 V1. And that's another downside of using these long expressions. You make mistakes. Anything else? Oh, sorry. Yes. U3 V3. Sorry. V1. All right. So what we're going to use is to define this thing called Kronecker delta, and what this symbol delta is. It has these two indices I and j. So for these two indices, the possible number of values that it can take is a total of 9 values. How is that 9 values? I could have delta 1, 1, 1, 2, 1, 3, or I could have delta 2, 1, 2, 2, 2, 3, and so on. So for each value of I going from 1 to 3 and each value of j going from 1 to 3, I'll have 9 possible different combinations. And the way we define that is simply that delta ij is equal to E1 or EI dot EJ. So if you were to list out all of these values, uh, you would get essentially all of these 9 terms, the ones in the brackets here, right here, right? And clearly this is delta 1, 1, which is 1. This blue term is delta 2, 2, which is 1. This blue term is delta 3, 3, which is 1. All the other terms, this one is delta 1, 2, 0, delta 1, 3, 0, delta 2, 1, delta 2, 3, delta 3, 1, delta 3, 2, all of them are 0. So out of the 9 possible values of this Kronecker delta, 6 of them are 0. Only 3 of them are non-zero. And that allows us to write this big, long expression in a more compact way. Okay? So what we are going to do is we are going to write this as, actually, let me move it back down. We are going to write this as a short form where I will use a double summation, I going from 1 to 3, j going from 1 to 3, ui vj ei dot ej. Does that make sense? If you can see this expression, this has 9 terms, which are all of these 9 terms that we listed up here. And that for each term of I, we have 3 terms of j. So that's how we get these 9 terms. And finally, we are going to use this definition of delta ij. So I'm going to replace this with delta ij. And I'm going to write that as sum I 1 to 3, sum j 1 to 3, ui vj delta ij. Now the very cool property of this Kronecker delta is, since most of the values of delta ij are actually 0. There were 9 values, 6 of them were 0. The way it helps us is that you can contract one of the indices out for the delta ij, meaning that I can take, for example, this j and this j, I can cancel those off and I can replace that with I. So what that means is that I can write that as summation of I 1 to 3, and at the same time the sum over j also cancels off. Okay, so I have ui vi. That's the contraction property of this Kronecker delta. So let me write that, contraction of delta ij. So this is a very useful property that helps us simplify complicated long expressions. And indeed, immediately you can see that what this has helped us to do is to write this as a sum of 3 terms instead of 9 terms. This is just u1 v1 plus u2 v2 plus u3 v3, which is indeed what a scalar product is, right? If I have 2 vectors, u and v, the dot product of u and v is u1 v1 plus u2 v2 plus u3 v3. We took a very long way to get there, but all of this exercise was to show you how you would use this type of a notation and this type of symbol to be able to work with these expressions quite often. So I will also mark this as a very important definition, that Kronecker delta is a symbol that we are going to use very often. And this property of this contraction of Kronecker delta is something to understand, something that you need to understand very well. So I'm going to repeat that a little bit here. We wrote Eij as delta ij. So if you look at the black markings here, that was the original expression that I had. Now we saw that there are two indices in delta ij, I and j. I pick any one of them. In this case, I pick j, and I said I'll take this j index, and anywhere else that the j index occurs, I'm going to take them and cancel them off with each other or contract them against each other. And this j will be replaced by the other index I of this delta ij. So the remaining index of delta ij goes to this point. And what I'm left with, uh, also after canceling off the summation over j, because j is being contracted, I'm left with only one summation and only i's in the index. And note once again, I have a summation over I, and the index I occurs only 2 times. Okay. So we'll use a lot of um, this notation as we go forward. And as you get more practice with it, you'll get better and better at it, and it will become almost second nature. But more formally, this notation that we have just been talking about is called the indicial notation. Why indicial? Because we are working with these indices I, j, and soon we'll have k, l, m, n, whatever. So the idea would be that in order to work with the component forms of vectors and later on tensors as well, we are going to use these indices I, j, k, so on. And we are going to write shorthand notations in this. The few properties of this notation that we must remember and must adhere to are the following: that any expression has, in general, two types of indices. One is called a free index, which occurs only once in a term. And if you write a equation, that free index will occur on both sides of the equation. Once on the left-hand side, once on the right-hand side. Okay. An example of this, I'll give you more examples of this. The other type of index is a repeated or a dummy index. You remember we just talked about these I and j and these repeated indices. These are examples of a dummy or a repeated index. I didn't have to use variable I could have used j, k, l, m, whatever, right? That's why it's called a dummy index. It it occurs exactly twice in a term, okay, and it does not occur on both sides of an equation. It denotes a summation. So as we just saw that every time, for example here, I was repeated twice and we had a sum over I. If we go back up, j occurred 2 times, j here, and there was a sum over j. So you will see that this thing happens quite often, that whenever an index is repeated, there is usually a summation sign over that. So we will use this convention, which is called the summation convention, that any time in an expression we see two i's or two j's or two indices, we'll assume that there is a summation over it. Okay, and what we'll write this as, we'll write this as, we're going to define this expression as simply vi ei. What we are, in doing this, what we are saying is that indeed this I is repeated, which means that, and the same thing here, which means that this summation is implied. Okay, so anytime I want to write this expression, which itself is a shorthand notation, but we want to make it even shorter. So in that sense, we are saying that whenever we see two indices, vi, ei, we are going to assume that there is a summation over there. If there is three indices, there would be instances where sometimes there are three indices I. In that case, it becomes ambiguous. In that case, we will explicitly have to write the summation sign. Okay, so this is just so that we don't have to write this summation sign and again. And actually, this convention or the summation convention was developed by theoreticians, physicians, really, Einstein in particular, among others, who found that this was the case, that every time I have two repeated indices, I am writing this summation sign and again and again. So in order to avoid all of that, they developed this shorthand notation. Um, all right. Finally, we'll make use of the Kronecker delta contraction property, and there are a couple of other symbols also we'll see later on today that we'll make use of to work with these types of expressions. So let's see how to use this summation convention and the initial notation. A vector V is equal to sum of its three components. I wrote that as a shorthand notation right here. And I'm going to define that in future I will write a vector V as simply this, VI, EI. And whenever I have these two repeated indices, I will immediately understand that yes, there is a summation also. I'm just not writing it. Okay, let's use that in an example here. An example of a case where we have a vector V and we want to find its projection along a unit vector n. Okay, so this n is a unit vector. I want to find its projection along this vector. How do I do that? Yes, we do need a theta there, but what we'll do is we'll drop a perpendicular from the tip of the vector down to the direction of that unit vector. So that's a perpendicular line. And the projection of that vector along that line would be another vector, which will be this particular vector. So this vector is what I'm going to call VP, the projected vector of V along n. Okay, V sub P. How do I find this V sub P? Okay, so let's say if we cos theta means essentially you are trying to use the dot product, right? So if I were to do V dot with n, that would be the that would be what? That would be the magnitude of this guy, right? So is that correct? VP vector VP is equal to V dot n. Is that correct? That's right. So on the left hand side I have a vector. On the right hand side I just have a scalar yet, right? This is just the magnitude of this vector VP is the length of that vector. So to get an actual vector, I need to take that scalar and multiply it with the unit vector n to get the projection of a vector. So that expression now is a projection of this given vector V along this unit vector n. And in order to write all of that in terms of components, I can do this. I can write V dot n. We just developed the dot product on the last page. So in terms of components, what would the dot product V dot n be? That's right, V1, N1, V2, N2, V plus V3, N3, right? And I will write that in shorthand notation. Summation I going from 1 to 3, VI, NI. Do I need to underline somewhere? No, because both of them, Vi is a scalar component of vector V, Ni is a scalar component of the unit vector n. The unit vector n has also three components, right? It has three components. It could be 1 over square root 3, 1 over square root 3, 1 over square root 3, for example. Right? So those ni's are the scalar components of that. That's the term inside the brackets. The term outside the brackets is simply n. And using our notation, I'm going to write that as VININ.
Should we say your dot product between n bar and the bracket?
You mean this bracket and n bar? So that would be a normal multiplication, right? It's the term inside the bracket is a scalar, right? The dot product is between two vectors. So that is the first type of, that's the scalar multiplication of a vector that we talked about. We have a scalar multiplying a vector. So no dot between them, indeed. Okay. And I'll point out once again, these two i's are repeated, which means that the summation is implied. I'm not going to write that summation explicitly, it's implied. Okay. All right. Similarly, if we want to find, let's say, the components of a vector, if I have a vector v, I have some coordinate system in terms of e1, e2, e3. Of course, we can take projections of that vector along e1, projection of that vector along e2, e3. All of those lengths would be the scalar components v1, v2, v3. How do I find that, or how do I express them mathematically in components? What we'll do is we'll consider exactly the operation that I just said. We'll take vector v and dot product with e1 to find v1, right? So essentially, on the left-hand side here, I have vi. Vi is equal to v dot product with ei. Now, couple of things here before I move on here. So first thing, this guy, I'm writing it in terms of I. So there are really three equations in there, right? This one equation represents, really there are three equations in there. Once when I is 1, 2, and 3. So when I write something like this, it means I'm writing three equations using this index I. And the other two things is that now I is what? I'm using I as a free index, correct? It occurs exactly once on both sides of this equation. We just saw a lot of these repeated indices, repeated or dummy indices, but here I'm using I. It occurs only once on both sides of an equation. Okay, and it of course represents three equations. So to work with that, we are going to again expand this V in terms of a repeated index J. So we can write this as, let's see, vector. I can write this as summation j going from 1 to 3 of Vj, and now I'll change the brackets Ej dot Ei. Of course, this is nothing but delta Ji or delta Ij, it doesn't matter. As long as the two indices are equal, it will be 1, and if it's not, then it's 0. And I'll write that as Vj delta Ji. Note that the summation over J is implied, and I will contract against that. I will contract against J. So J and the summation will cancel off, and I will replace the index I with the index over the expression, so that would become Vi. Indeed, that's exactly what we had started with, so no surprises there. But this is a sort of an example of how you would work with free indices and repeated indices. All we did here was to show that a component v1, for example, would be given by the vector v dot with e1, and essentially, as I mentioned, since I is a free index, you can take all of that derivation, the entire derivation, you can take that and repeat it 3 times. Once for I1, I2, and I3. So it's a very shorthand way of writing a very long, not a very long, but a reasonably long derivation in terms of these indices. Okay, questions? This will take some time for you to digest, and I'm sure I'll get you a lot of practice on this with the homeworks. So if you have questions, definitely you should ask. Okay. All right. Here's a couple more examples. The norm of a vector or the length of a vector, which I previously said was indeed the dot products and square root. In the same way that I and I are repeated, the summation is implied. I can write that as square root of ui ui. And that is indeed how we calculate the norm of a vector. So here's a question. What is delta I? Say again? 3. 1 or 3? 3, right? Indeed, delta I is 3. Why is that? That's right, because there are 2 i's in there, which means what I'm writing here really is summation of delta I going from 1 to 3, which means what I'm writing is delta 1 1 plus delta 2 2 plus delta 3 3. Each one of them is 1, so I get a total of 3. All right, so it's easy to be kind of confused or make mistakes like delta I is 1 or something, right? You have to pay very close attention whenever you have a repeated index or whenever you have a free index. Okay. All right, so I think we might just have time to go through this cross product. Last question. Okay, the last type of vector product that we are going to look at in terms for 2 vectors. If I have u and v, the cross product, as you know, according to the right-hand rule, is you take vector u and you cross it towards v, and the result, according to the right-hand rule, is points in the plane perpendicular to u and v. And maybe just to be technically, if I'm drawing it the way I should have u here, v here, so that u cross with v gives me a perpendicular out of the plane of that plane. So although this is a 3-dimensional figure, so but essentially, yes, the cross product, the magnitude of the cross product vector would of course be the area of the parallelogram formed by u and v, which you know well, and the direction is given by the right-hand rule, as you know well. Now, in terms of components, if I were to do that, this will take some more operations like that. U cross v, we are going to take u, description of u in terms of I, description of v in terms of j. We'll have the same 9 terms. So let me see if I can borrow some of those terms rather than having to repeatedly write that. I don't know about you, but I'm tired of writing those 9 terms. So I'm going to copy all of that. Paste it here. And what we have here then is all of those 9 terms where we have u1, v1, u2, u1, v2, and u1, v3, and so on. But instead of having a dot product in the brackets, I have a cross product, right? And indeed, according to the cross products properties, we have E1 cross with E1, if I have two unit vectors pointing in the same direction, of course, the cross product is 0. So all the diagonals in this case are 0. For the dot product, or the diagonals were 1. But here they are all 0. When we have E1 cross E2, we get plus E3. When we have E2 cross E1, we get minus E3. So all the positive components I have written in this blue. All the negative components I have written in this purple. So essentially, for all of these 9 terms, 3 of those end up being 0. 3 of them end up giving us positive unit vectors, and the last 3 give us negative unit vectors. I'll let you digest this for a little bit, and of course all of these notes will be up online, so you don't have to worry about copying all of that. But now the question becomes, for the dot product, we had something called the Kronecker delta that allowed us to shrink the expression quite a bit. What can we do about this? So here we have these 3 terms that go to 0, 3 to plus unit vectors, 3 to negative unit vectors. And to be able to work with these types of expressions, we are going to come up with a symbol that is called an alternating symbol, or a permutation symbol, or a Levi-Civita symbol, which we are going to denote as epsilon I, j, k, 3 indices, okay? And which we are going to define as, so every time I write 3 equal to, sort of 3 lines with the equal to, that means defined as. So I'm going to define that as EI cross EJ dot EK. Okay, so let me ask you this. How many equations are in there in that expression? 27. For each value of I, I'll have 3 values of j and 3 values of k. So 3 times 3 times 3. There are 27 equations in that small box. Okay? So, and you have to learn to interpret it that way, because that's the whole point of using this initial notation. If you were to list them out by hand, we'd just be doing that for the rest of the semester. So indeed, there are 27 equations right here. And the good thing is that not all of them are useful. Only very few of them are useful. The way that we are going to define that symbol is that anytime I have any of the 2 indices the same, for example, I could have epsilon 1, 1, 1. The value of that would be 0. Epsilon 1, 1, 2, 0. Epsilon 1, 1, 3, 0. Right? So in that way, there are how many of those terms that turn out to be 0? Yeah, in total there would be 21 terms that would turn out to be 0, right? And the value of that epsilon ijk would be positive 1 if I, j, k, the 3 numbers, whatever those 3 numbers are, they happen to occur in a cyclic order, something like either 1, 2, 3, or 2, 3, 1, or 3, 1, 2. So maybe I should write that. Epsilon 1, 2, 3, epsilon 2, 3, 1, and epsilon 3, 1, 2. Those 3 equations would be basically, if you go in here, you can plug in 1, 2, 3. So for example, epsilon 1, 2, 3 would be E1 cross E2. What is that? E1 cross E2. Cross product between E1 cross E2 gives me E3, right? E3 dot with E3 gives me
1.
plus 1, right? So maybe I should write that here. Epsilon 1, 2, 3, which is defined as E1 cross with E2 dot with E3. That is indeed equal to 1, plus 1. And similarly, you can check with the other 2 combinations of this. 2 cross 3, E2 cross E3 gives me E1, E1 dot E1 is 1, and so on, right? And in the same way that the other three negative numbers are obtained as a counter and anti-cyclic case, where I would get sequences like 321 or 213 or 132. So all of those numbers would be negative ones. So 321, 213, and 132. So in that way, these are the only 6 non-zero values of this permutation symbol. Even though there are 27 possible values, 21 of them are zero, only 6 are non-zero, and that allows us to write an expression something like this in a much more compact way, but it looks like I've run out of time here. So let's stop here. I'll complete this out next time on Monday. Monday is not a holiday, right? I think Labor Day is the following week. Okay.